Today we are in 3.3, evaluating limits, and this time we're going to do it in an analytical way. So in 3.2 we introduced the idea of limits, and we were making tables and looking at graphs, and essentially what we were doing was making an estimate. And so we want to be able to do this more precisely. That's a nice way to introduce limits because you get the understanding of what a limit is, but now we need to do it in a way that's not just guessing. So we know that from 3.2 that the limit as x approaches c of f does not depend on f of c. That basically means that it doesn't matter if that point is not there, if it's undefined, if it's somewhere else, as long it doesn't, the existence of this point does not matter or impact this limit at all. However, sometimes the limit is precisely f of c, and basically we can just evaluate it by direct substitution, which just means plug in the value of c into my function. So well-behaved functions that are continuous at x equals c can be evaluated directly, meaning the limit as x approaches c of f is just plug in the c value and get the answer. Okay, so some basic limit laws when f of x is continuous at c, meaning that when I plug in c, I'm not dividing by 0, I'm not taking the square root of a negative number, it's not part of a domain restriction on f, then I can just plug in the c. So my first one here, so in all of these cases, I'm thinking that b and c are just real numbers. So the limit as x approaches c of b is equal to b. So b is a constant. So this seems kind of odd, but if you think about it, for instance, I'm thinking of if y equals 2, right? If I looked at the limit as x approaches any number of y equals 2, so if I think graphically speaking, y equals 2 is a horizontal line, right? So it doesn't matter what value of c I'm approaching, like maybe I wanted x to be 1 and I want to see, oh, well, what's it approaching? Well, it's always approaching 2. Okay, so the limit of a constant function really is what this is. A limit of a constant is just the constant itself. So, right, it doesn't matter what value I'm approaching, the limit as x approaches any number is still always going to be this y value because it's constant all the time. So, if I had the limit as x approaches 6 of 2, this is still 2 regardless of what value I'm going to here. Right, so this is just an example of it. All right, so if we have the limit as x approaches c of x, and this is completely continuous, then we can just directly substitute c in for x and we get out c. So for instance, if I wanted the limit as x approaches 2 of x, here my answer is 2. Maybe I should choose it. Let me choose 3 this time, just so I'm not using the same number all the time. I have the limit as x approaches 3 is 3, because if I think of the graph of y equals x, right? So as I approach 3, right, that's my 0.33 up there, and as I approach from this side, and as I approach from this side, I'm still approaching this y value over here, which is also 3, right? Because when I plug in x is 3, that's what I get out for y. It's like if I have this, right, when I plug in 3, then I get out 3. So as long as I can just, right, nothing bad happens here when I plug in the c, I just plug in the c. That's it. All right, and then the last one is if I have the limit as x approaches c of x to the n, and here we're assuming that n is a positive integer, like it's a positive whole number, then my number is just c to the n. So if I look at the limit as x approaches 4 of x to the n, then I just have 4 to the n here, right? Whatever n is. Like if I had the limit as x approached 4 of x to the second power, x squared, then this is 4 squared, which is just 16. Right? It's just direct substitution. All right, so that's great, right? It's really nice when we can direct substitute, and so we should always kind of look for that first. And then we also have some properties of limits that we can use, whether or not it's continuous there or not. Okay, so we're going to let b and c be real numbers and n be an integer, okay, a positive integer. So we're going to let f and g be functions that have the following limits. So it may or may not, they may not or may not be continuous at x equals c, but the limit does exist there regardless, whether it's continuous there or not. So if we know that f has a limit, then we can multiply it by anything, right? That means that the limit as x approaches c of b times f of x is just, we already know that the limit as x approaches c of f is L, so if we're just multiplying by a constant, we just multiply the limit by the constant as well. So if I knew that the limit as x approaches 2 of x is 2, then if I multiplied this, right, then I have the limit of 3 times x as x approaches 2 would be 3 times 2. It's just really this constant, I could actually write it like this, 3 times the limit as x approaches 2 of x, which we know is 3, and then times L, which is 2. So we're allowed to just multiply it, right? If the limit exists, and then we have just some constant multiplier next to it, we just multiply the constant by the limit. All right, so we also have the sum and difference. Now this is really important to us. These seem really kind of basic, but everything in mathematics is very carefully defined, right? Nothing is ambiguous in math, so everything is very precisely defined. And so it sort of makes sense that we can do these things, but really we have to define them very carefully because not everything in math can we just add and subtract at will. Okay? So if we have, again, the limits existing of f and g, and we're adding them together, then as x approaches c, we can actually look at them separately. This actually means that we can look at the limit as x approaches c of f, and then also the limit of x approaches c of g. Right? So we can break them apart and look at them individually. This may not seem that interesting, but it's actually really a nice thing when you start getting complicated functions that you can look at them separately. And so basically this one is already, we know, is L from up here, and this one up here is K, so this is literally L plus K. Okay? These are just numbers. All right, so the same thing when I have multiplication. This is a really nice one when we have a product of things. When I have the limit of f and g multiplied, then I can look at each one separately. It can make things much easier. So basically I can look at this and then times the limit of this. So I can look at each piece individually, assuming that their limits do exist. So if I have this times this is literally L times K because the limit, this is equal to L, this is equal to K, and there's a multiplication symbol in between. So I multiply the two limits together. All right, same thing applies if I have a quotient, right? Again, I'm still knowing that the limit as x approaches c of f is L, the limit as x approaches c of g is K, and so if I have a quotient, I can look at them separately, and it's just L divided by K. That's provided that K can't be 0, of course, because K would make division by 0. Okay. So if I had the limit as x approaches c of 2x over 4x squared, right, I can look at the limit as x approaches, well, let me give this a number. We'll put in 1 here. Limit as x approaches 1 of 2x, which is, this is the constant multiplier rule already, which is 2 times 1, because I can direct substitute in here because this is a nice polynomial continuous function. And then I can also look at the limit as x approaches 1 of 4x squared. Again, another direct substitution, right? If I plug in 1, nothing, I'm not dividing by 0, and this gives me 4. And so my limit as x approaches 1 of 2x over 4x squared is 2 over 4. So I can literally look at them separately. Now this is a really basic example, but sometimes my functions get more complicated, and it's a very useful tool. All right, and then the last thing that we can do is also use it as a power. So if I know that the limit as x approaches c, we can actually put the limit inside places. So we can kind of think of this as the limit as x approaches c of f of x to the n. So we can evaluate this limit on the inside, which is L, and raise it to the nth power. So that just means that we can, if I have the limit as x approaches 3 of x to the 4th, right, we can think of this as so I can think of this as the limit as x approaches 3 of x raised to the 4th. So I know that this is that direct substitution. So this here is 3, right? This limit as x approaches 3, I'm allowed to plug in 3 into x, and I just get 3 to the 4th then, which is 81. Right? So I know that those seem sort of obvious, but they're not always obvious. And again, you can only use these when the limits exist. So if the limit is infinite in either one of these cases, or it fails to exist in any way, then these limit laws do not apply. So there are specific rules when we can use them. All right, so again, you know, we've really, at least I've come to really like polynomial functions. I hope that you have too, because limits of polynomial functions are really nice. Because polynomials functions have those nice, smooth, continuous graphs that always have a domain of all real numbers, which means that for any polynomial, if we're looking at the limit as x approaches some value, you just plug in the value. So polynomial functions are continuous everywhere, so that means when we look at the limit anywhere, we can just plug it in. So the limit of any polynomial as x approaches c is p of c. So you just plug it in the function. Now rational functions are almost just as nice, except for they involve the division. So remember, our rational functions are like the numerator and denominator, which are each polynomial functions. So again, we can just plug in c, assuming, of course, that d of c isn't 0. Okay? So rational functions are nice, smooth curves as long as the denominator isn't 0. So they're nice and smooth, continuous everywhere. We're going to talk about continuity more in detail in just a couple of sections. But they're nice, continuous functions that are continuous everywhere except for my division of 0 places. So I'm allowed to plug in this c everywhere except for where it's equal to 0. So if I had the limit as x approaches 1 of x squared plus 1 over x plus 2, right, in this case, right, if I was looking at the limit as x approaches negative 2, I would have a problem, right? Then I can't just directly plug it in. But since I can plug in 1 and I get that 3 in the denominator, there's no reason why I can't just directly substitute. So 1 squared is 1, so I get 1 plus 1 over 1 plus 2. So this is just 2/3 directly. Right? So if I come up here, I didn't really do a polynomial example, but I had the limit as x approaches 2 of 3x squared minus 4, then this is a polynomial that I can just directly substitute. So this is just equal to 3 times 4 minus 4. So I end up with 12 minus 4, which is 8. Okay? So that's what's really nice when I'm working with polynomial functions. I just plug in the value. If I'm working with rational functions, I always try to plug in the value, assuming I don't get denominator equals 0, then I can do that. So we'll talk about strategies in the next lecture on how to deal with it if I plug it in, I would be dividing by 0.